Hi everyone. So in this section, we're going to be looking at trigonometric integrals, meaning integrals where you have a trigonometric expression. So in this video specifically, we're going to be focusing on trigonometric expressions where you're either multiplying together powers of sine and cosine or powers of tangent and secant. So let me write that down. So in this video, we're focusing on integrals of the form so sine to the m of x times cosine to the n of x dx, and the other one would be integrals of the form tangent to the m of x times secant to the n of x dx. And so what we'll see about these format of integrals is that basically we can really take advantage of some trigonometric identities, as well as the fact that there's a relationship between sine and cosine and their derivatives, as well as tangent and secant and their derivatives. So we'll be able to really make use of those different facts and evaluate these integrals. And then in the next video, we're going to focus on some slightly different types of trig integrals. So the first thing I want to talk about is just to remind you of a couple of trigonometric identities that we're going to be using in this section. And we'll talk about some other trig identities in the next video. But today I'm just going to bring up the ones that are relevant to what we're doing here. So the first one, which is probably the most important one to know, is that if you have sine squared of a variable plus cosine squared of that same variable, that's equal to 1. So that's what's called the Pythagorean identity. So where does that come from? Really, it just comes from the fact that if you remember how trig works on the unit circle, any point that you go to on the unit circle, if you're at an angle of, let's call this angle, I'm going to call it theta so that it doesn't get confused with the x and y coordinates. So if you're at an angle of theta, then the x coordinate of the point is going to be cosine of theta, and the y coordinate of the point is going to be sine of theta. And so because we're on the unit circle, the x coordinate squared plus the y coordinate squared is equal to 1, right? That's the equation of the unit circle. And so because this point lies on the unit circle, it's going to be true that cosine squared of theta plus sine squared of theta is equal to 1. So that's where this identity comes from. And so this identity, there's a couple of different ways that you can kind of rearrange this that will be useful to us. So one of those will be saying, if we want to express sine squared, we can write it as 1 minus cosine squared. And then if we want to write down cosine squared, we can express it as 1 minus sine squared. And then there's a couple more that you can get from, so if you start with this Pythagorean identity and you go through and you divide every term by either sine squared or cosine squared, that's going to give you 2 more Pythagorean identities. And there's really only one that we're going to be using in this class, so I'm just going to write down that one. So if you take this equation and you divide everything by cosine squared, you would get tangent squared of x plus 1 is equal to secant squared. And so we'll be using this one a lot too. And so it's already solved for secant squared. So secant squared is the same thing as tangent squared of x plus 1. But if you ever want to express tangent squared in terms of secant, we know that tangent squared of x is going to be equal to secant squared of x minus 1. So we'll see how these come up in a little bit. Okay, so let's jump into an example. So the first example we're going to do is actually going to be one that we've done in the past. So I just want to kind of remind you of one way that trig integrals can kind of play out, and then we'll see some variations where we'll have to actually use the identities I mentioned. So let's say you wanted to integrate sine squared of x, sine squared of x times cosine of x. dx. So this was actually, I think this even might have been on your first midterm, or at least something similar to this was. So what do we do here? We do a substitution, right? And so because sine squared of x, that's the same thing as sine of x squared, we can let u equal sine of x, and then du is going to equal sine of x, or sorry, cosine of x dx. And by the way, I think now that we are using integration by parts, typically we use u and v for that. So if you want, you can always switch to w for substitution, but it doesn't really matter. As long as you're not using both methods in the same problem, you can just use u for this as well. Okay, so what does this give us when we put it back? We end up with u squared times cosine of x times du over cosine of x. So that gets rid of our cosines, and now we're just left with the integral of u squared du. And so now we have a polynomial, right? U squared, we know how to evaluate that. That's going to be u cubed over 3 plus c. And then we put back in our original input, or original u, which was sine of x. So that becomes sine cubed of x over 3 plus c. Okay, so this one we can do just using substitution. So now I'm just going to make one small change to this integral, and we'll see how that is going to force us to do something a little bit different. So let's say now that we're going to be trying to evaluate the integral of, so it's still sine squared of x, but now let's multiply that with cosine cubed of x. So if we try to just do the same substitution as before, we're not going to be able to quite finish off the integral, because basically we'll still be able to cancel out one cosine, but we would be left with cosine squared. So we are going to eventually do a substitution, but there's something else we need to do first. So the first thing I want to do is take cosine cubed of x, and I'm going to split it apart into cosine times cosine squared. And we'll see why that is in a second. Okay, so why is this useful? Well, because this cosine, we know we can get rid of that one by doing the same substitution, right? If we let u equal the sine of x, that will get rid of this cosine. What about the cosine squared? How can we deal with that? Well, we know that we have an identity that lets us express cosine in terms of sine, right? So what we can do is we can use the identity here. So we know that cosine squared of x is 1 minus sine squared of x. And so we'll be left with, now if we put that in here, we'll have the integral of sine squared of x times 1 minus sine squared of x times cosine of x dx. And so now, because everything is written in terms of sine except for this extra cosine, now we can go ahead and do the same substitution we did in the last problem. So if we let u equal to sine of x, and then du is equal to cosine of x dx, well, now let's see what that gives us. So now we have the integral of u squared times 1 minus u squared times cosine of x times, and I didn't quite solve this, so this means that du over cosine of x is equal to dx. So then we can put in du over cosine of x. And so we're left with now something that we know how to integrate, right? We have the integral of, so we can distribute here, and this will be u squared minus u to the fourth du. And so this is going to give us, if we take the antiderivative of each piece, we have u cubed over 3 minus u to the 5th over 5 plus c. And then we just have to put back in our original u, so that is going to be sine cubed of x over 3 minus sine to the 5th of x over 5 plus c. And that would be our final answer. So this same approach that we just did is basically going to work on any integral that kind of looks like the one that we started with, as long as the exponent on cosine is odd. So I want to show you another example, but let me just kind of write that down as a sentence. So this same approach will work for any integral of the form, the integral of sine to the m of x times cosine to the n of x dx, where n is an odd number. And so why does it have to be odd? Well, basically, let's think about what happened here. So we pulled away one copy of cosine, right? That copy of cosine was what allowed us to do the substitution, right? If we didn't have this one cosine on its own, we wouldn't have been able to get rid of this cosine here. Or sorry, we wouldn't be able to get rid of this cosine here. And then we need the additional part to be even so that we can rewrite it using this identity. So next I just want to look at an example where it's not just going to be a cosine squared, it's going to be a different even power of cosine, but we'll see that we can still use the same approach that we used in this example. So the next few examples, and this is going to be true I think for the remainder of the video, I'm not going to completely finish off these integrals, because once you get it in terms of u, I think at this point you are, comfortable evaluating something like this, right? So really the only tricky part with these integrals is getting them to that point. And so that's what I'm going to focus on. I'm just going to kind of leave them once we get to that point, just so I don't kind of make this video excessively long. So another example where this would work. So let's take the same, very similar to what we just did, but now let's make it sine squared of x times cosine to the 5th of x dx. So we're going to do the exact same thing. We're going to start by pulling out one copy of cosine. So I'm going to rewrite this as cosine to the 4th of x times cosine of x dx. Okay, so now we have to figure out how to kind of use an identity to get rid of this cosine to the 4th of x, to express it in terms of sine squared. And so because this is an even exponent, anytime you have an even exponent, that means that you can write it as something else squared, right? So cosine to the 4th of x is equal to cosine squared of x squared. Right? And if it was cosine to the 6th, then it would be cosine squared of x cubed. And if it was cosine to the 8th, it would be cosine squared to the 4th. So you always want to have the squared part on the inside, because that's what we're going to replace with the Pythagorean identity. But then this number here is going to vary depending on what power you had here. So you're basically just saying, cosine squared and then raising it to whatever power you need to raise it to in order to get the same number you had here. Okay, so how can we rewrite this now? Well, we know that cosine squared of x is the same as 1 minus sine squared of x. And now we have that squared. So now we can go ahead and put that in. And so now we'll have sine squared of x times 1 minus sine squared of x squared times cosine of x dx. And so now we can use the same substitution that we used in the previous example. So if we let u equal to sine of x, du is equal to cosine of x dx. So du over cosine of x is equal to dx. Okay, so let's see what that looks like. So now we're going to have the integral of, again, so u is sine of x, so that's going to be u squared. And then here we have 1 minus u squared squared. And then we have cosine of x, and we have du over cosine of x. So once again, as planned, these cancel out, and now we're left with something that's all in terms of u. And so how would you actually go about evaluating this? Well, you would have to multiply everything out, right? You would want to figure out what is 1 minus u squared squared, multiply that out, multiply it with u squared, and then you'd have a polynomial that you know how to evaluate. So I'm just going to leave it here and trust that you would know how to kind of go from here. But yeah, this will work for any time that you have an odd power of cosine. And I want to just show you one more example that's a little different, but show you that it still works. So let's say you just had the integral of cosine to the 5th of x. So this time there's no sign, right? And so really it still actually fits with this format here. It's just that the exponent on sine is 0, right? Because if you take something and raise it to the 0, you get 1. And so it still fits with this. It still has an odd number as the exponent for cosine. And so this approach will actually still work. So again, we just want to split this apart. So we would write it as, and let's actually, you know what, I had it written in my notes as this, but I'm going to change it so that we see something a little different. So let's say cosine to the 7th. And so that would leave us with cosine to the 6th of x times cosine of x dx. And so now we need to figure out how to deal with this. Well, cosine to the 6th of x is the same as cosine squared of x cubed. And cosine squared of x, we know that that's 1 minus sine squared of x. And so we can put that in. And so even though the integral initially did not have any signs in it, we can introduce signs, and then that will allow us to actually do the substitution. So we're going to have 1 minus sine squared of x cubed times cosine of x dx. And then from here, again, you would just use the same substitution. So u is equal to sine of x, du is equal to cosine of x dx. Du over cosine of x is equal to dx. And so what would this end up looking like? It would be the integral of 1 minus u squared cubed times cosine of x times du over cosine of x. And so again, you would be left with something that's just a polynomial. You would have to multiply it out. So you would have to do 1 minus u squared, multiply that with itself 3 times. But then you would have a polynomial that you know how to evaluate. Okay, so let's write this down as kind of a general rule, and then we'll see that there's basically an opposite version we can do if the roles of sine and cosine are flipped. So basically the approach I want to write down is that anytime, so let's say general strategy for trig integrals. Oops, let me just not do that part. Okay, so first case is if you have an integral of the form sine to the m of x times cosine to the n of x. So we have kind of two cases here. So the first case is the one that we just saw. So if cosine has an odd power, so if n is odd, what you're going to do is you're going to save one factor of cosine. So when I say save, I mean you kind of pull it aside like we did in the last few examples. And then because it's an odd number, when you've pulled one aside, you're left with an even number, right? And so you're going to express the remaining factors of cosine of x as, basically I'll say it this way, using the identity cosine squared of x is equal to 1 minus sine squared of x. And then you're going to use the substitution u is equal to sine of x. Because basically you're translating everything in terms of sine of x, so it makes sense to use that substitution. So if they're flipped, it's basically just the opposite. So let's write that down and then we'll do a quick example like that. And then we'll get into some involving tangent and secant. So that will be a little different. So if m is odd, so that would be if sine is raised to an odd power, we're going to save one factor of sine of x. We're going to express the remaining factors of sine of x using the identity so now we're trying to express sine of x, so we're going to use the identity sine squared of x is equal to 1 minus cosine squared of x. So we're translating our sines into cosines. And then we're going to use the substitution this time you would be letting u equal cosine of x because you're translating everything into cosine of x. And by the way, if they're both odd, then you can do either one. So it doesn't really matter which one you choose if they're both odd. But if only one of them is odd, then it kind of forces you to go one way or the other. So let's just real quickly look at an example of what happens when sine and cosine are switched. I don't want to spend too long on this because it is very, very similar to what we've already seen. But let's say, for example, you're trying to evaluate, sorry, I lost my notes here. Okay, so let's say that you're now evaluating cosine squared of x times sine cubed of x dx. So again, we can break this up into cosine squared of x times sine squared of x times sine of x dx. And so then how do we get rid of this sine squared of x? Well, we can use the fact that sine squared of x is equal to 1 minus cosine squared of x. And so that will give us the integral cosine squared of x times 1 minus cosine squared of x. And then we still have this sine of x. And so in this case, because everything's in terms of cosine and we have this extra factor of sine we want to get rid of, we use the substitution u is equal to cosine of x. And then there's just one thing that goes differently, right? Because the derivative of cosine is actually negative sine. So du is equal to negative sine of x dx. So we're basically just going to have an extra negative sign floating around. And so if we divide both sides by negative sine of x, that tells us what our dx is. And so the integral is going to become the integral of u squared times 1 minus u squared times sine of x times du over negative sine of x. And so the sine of x's cancel out, but we have this extra negative sign that we can't forget about. So we're going to be left with now the negative integral of u squared times 1 minus u squared du. And so again, you would just multiply that out and go from there. Okay, so now I want to talk about integrals that are of the form involving powers of tangent and secant. So these ones are a little bit different just because of what the derivatives are of tangent and secant. So I want to first just remind you of that. So reminder, so what is the derivative of tangent? It's secant squared. So what that means is that if we're doing a substitution where we're letting u equal the tangent of x, we're actually going to have a squared secant of x come in. So it's going to be a little bit different than what happened with sine and cosine. And then if you take the derivative of secant, well, that derivative is actually secant of x times tangent of x. So again, a little bit different in how these are going to play out, but basically what we're going to take advantage of here is, if we go back to these identities, notice that it kind of works out nicely, right? Because sine and cosine are linked together by this trig identity, and then they're also related to each other via derivatives. And then same thing here, tangent and secant, they're linked together using this identity, but they're also related to each other by derivatives. So, we'll be able to take advantage of that the same way we did with sine and cosine. Okay, so let's do an example. So again, similar to what we did with the other ones, we'll start with kind of a simple example, and then we'll get into ones where we have to do a little bit more work with identities. So let's say that we're trying to integrate tangent cubed of x times secant squared of x dx. So in this case, if we let u equal tangent of x, then du will equal secant squared of x dx. And so du over secant squared of x is equal to dx. And so this one, you don't have to do anything with identities. You can just do a u substitution straight up. So we get u cubed secant squared of x times du over secant squared of x. And so you would just be left with the integral of u cubed, which you can take it from there. So now let's try to do one where we're gonna use this same substitution, but there's gonna be kind of an additional step to it. So now let's say that we're trying to integrate tangent cubed still, so it's still gonna be tangent cubed of x, but now let's multiply it with secant to the fourth of x. Okay, so if we want to do a substitution like we did on the last one, we need, if we're going to let u equal to tangent, we need a secant squared, right? That is what the derivative of tangent is, and that's what we'll be able to cancel out. And so just like how with the sine and cosine ones, we just pulled aside one sine or cosine, here we have to pull aside actually a secant squared because that's our derivative. So we can rewrite this as the integral of tangent cubed of x times secant squared of x times secant squared of x dx. And so then one of these secant squareds, that's where we want to go and use the identity, right? And so our identity for tangent and secant says that secant squared is equal to 1 plus tangent squared. So we can rewrite secant squared as 1 plus tangent squared of x. And so that will give us now the integral of tangent cubed of x times 1 plus tangent squared of x times secant squared of x. And so now we have everything in terms of tangent except for this derivative that will go away when we do substitution. So we're all set up for substitution again. So same substitution, u is equal to tangent of x, du is equal to secant squared of x dx. You know how it goes from there. So now let's just do that substitution. So we end up with u cubed times 1 plus u squared. And then the secant squareds of x are going to cancel out. I'm just going to skip writing that step and we'll be left with du. So yeah, basically it plays out the same way. If this had been, let's say, secant to the 6th, then we would have been left with a 4th here, right? And so we would have had to take this whole thing and square it. So same idea that happened with the other one. As long as what you're left over with is an even power of secant, you can express it as secant squared to some power. So let's write this down as kind of a general rule, and then we'll see how it goes when when we reverse the roles of which substitution we're doing. Okay, so we talked about this form. So let's talk about now the other form. So if you have the integral of tangent to the m of x times secant to the n of x dx. So again, we're going to have two different cases here. So first case would be if n is even. Sorry, I'm just grabbing my notes to make sure I write everything down right here. So if n is even, then we're going to do basically what we just did. We're going to save a factor of secant squared. And so if you pull aside that secant squared, if n is even, you're still left with an even number of secants. And that's what you need, because you need to be able to express it as secant squared to a power. Then we're going to use the identity. So we're going to express, how did I say it here? Actually, let me see. Express the remaining factors of secant of x using the identity secant squared of x is equal to 1 plus tangent squared of x. And then we're going to use substitution with u is equal to, in this case, we would do u is equal to tangent of x. Okay, so what's going to be the other case? Well, it's a little bit different from the other one. So now we're going to say if m is odd. So if the power of tangent is odd. So just like with the sine and cosine, there are some cases where you could actually use either approach. So actually the example that we just did, this power was odd and this power was even. So we actually could use as well the next approach I'm about to write down. So if m is odd, what you're going to do instead is you're going to save a factor of secant times tangent. And we'll see how this plays out in an example in a second. So what are we going to do after that? We're going to express the remaining factors of tangent of x using the identity tangent squared of x is equal to secant squared of x minus 1. And then we're going to use substitution with u is equal to secant of x. So I know like all of these different rules might feel like, oh, they're all kind of similar and different and how you have to remember all the different even or odd powers. Really, I think if you just practice these, you'll kind of get a vibe for what's going on. Like it really just has to do, this whole even and odd business really just has to do with what the derivatives are in these different types of integrals. And that will kind of force you to only be able to use one specific type of substitution. So let's look at one last example. So this is going to be now, we actually could just do the same example because like I said, all that needs to happen is the exponent on tangent needs to be odd for us to use this next approach, but let's do a different example just to kind of make things a little bit more interesting. So let's do the integral of tangent to the fifth of x times secant to the seventh of x. Okay, so so one thing I've noticed is that the exponent on secant is odd. And so that means we're not going to be able to use the same approach we used here, right? Because you can only use this approach if you first separate out secant squared and then you're still left with something even. And that's not going to happen here. If you tried to separate out secant squared, you'd be left with secant to the fifth. And so you wouldn't be able to use that identity that we used above. And so what we want to do instead is separate out a tangent times a secant. And we're going to do the other substitution. So if we separate out a tangent times a secant, we'll be left with tangent to the fourth of x times secant to the sixth of x times secant of x times tangent of x. So this part here, this is the derivative of secant. And so that tells us that eventually the substitution we want to use is u is equal to secant of x. So in order for us to use that substitution, that means that we need to take this tangent part and switch it to being in terms of secant. So the thing you're doing over and over is basically just, separating something out and then seeing what substitution you need to use and then changing everything to be in terms of whatever you're substituting. So in this case, that means substituting the tangent to the fourth to be in terms of secant. Okay, so what is our identity that we're going to use in this case? Well, we know that, first of all, we need to say that tangent to the fourth of x can be written as tangent squared of x squared, right? And then what is tangent squared of x? Well, we know that tangent squared of x is equal to secant squared of x minus 1 squared. And so now we can go back into this integral and rewrite it as secant squared of x minus 1 squared times secant to the sixth of x times secant of x times tangent of x dx. And temporarily this looks like a much more complicated integral, but now we're pretty much done. So now what do we have to do? We just have to let u equal secant of x. And so that means that du is equal to secant of x times tangent of x dx. And so therefore, du over secant of x tangent of x is equal to dx. So let's see what this makes our integral look like. So now we're going to have the integral of, so for secant of x, that's going to, here this first part is going to be u squared minus 1 squared. And then we have u to the sixth. And then we have secant of x, tangent of x. And then we have du over secant of x, tangent of x. And so as has been happening, our substitution works out. And so now we just be left with, again, a polynomial. So you would just need to multiply out whatever u squared minus 1 squared gives you, multiply that with u to the sixth, and then you'll be ready to integrate. And then just remember at the end that you have to put back in whatever u was, right? So that's one thing I just want to mention since we haven't been doing these examples, is that because they're all different trig integrals, even though after our substitution, these all kind of look the same, they'll actually give you different types of expressions at the end of the day because the substitution you made was actually different. So that is it for this video. Like I said, in the next video, we'll get into some different examples of basically trig expressions that are not of this form that we saw in this video. And definitely check out the worksheet for today. I put a couple of examples that go a little beyond what we saw in this video. So some problems where you have to use substitution kind of twice. So that's the last two questions that you'll see on the worksheet. I would definitely recommend checking those out. All right, I'll see you next time.